Module 3, Protocols and Models. So networks can vary in size and complexity. They can be as complex as devices connected across the internet, or as simple as two computers directly connected to one another with a single cable and anything in between. It is not, however, enough just to have a connection. Devices must also agree on how to communicate. So there are three elements to any communication. There will be a source, which is the identified sender. There will be a destination, which will be the identified receiver of the information. And then there will be a channel or media that provides for the path of communication to occur. So for this course, fiber, copper, or wireless. All communications are governed by protocols. So protocols are the rules that communications will follow. They will vary depending on the protocol in place. So in the human network, as an example, if I were going to have a conversation with somebody and I spoke English and French and they spoke English and Spanish, we would agree to speak English because that is what we both understand. So all throughout your communications path, this is what is going to happen throughout. Now, individuals must use established rules or agreements to govern the conversation, as I just gave you an example. So in this example, the first message is difficult to read because it is not formatted properly, whereas the second one is put into the correct format and can be easily read. Same thing in the data network. So some rules for establishments. Your protocols must account for the following requirements and be in agreement on the following: an identified sender and receiver, who is generating communication, who is receiving the communication. Common language and grammar, things like message encoding, message formatting and encapsulation. Speed and timing of delivery, so how large is the message, and what is my message timing? How quick can I push this through? Confirmation or acknowledgement requirements, whether or not message delivery options are needed for this particular conversation. Now, encoding we talked a little bit about. It is the process of converting information into another acceptable form for transmission. So encoding happens at the source. Decoding would happen in the reverse order at the destination as they were decapsulating the information. When a message is sent, it must use a specific format or structure. So message formats depend on the type of message and the channel that is used to deliver that message. So again, in the human network, if you refer to just a letter that you're sending to somebody here on the left, your actual data is the letter that is contained in the envelope. Here is the generator of the information. Here is the receiver of the information. And again, then we have your data. So the generator would be the source, and the receiver would be the destination. On the right-hand side of this slide, you see a visual. We're going to start looking at visuals that have to do with frames, that have to do with packets of information. So this is an example of a packet, an IP4 packet. So things we want to pay attention to on this slide, the purple areas. Purple for version, it's going to mean either IPv4 or IPv6. Source, again, the generator of the information. Destination, the receiver of the information. So encoding between hosts must be in an appropriate format for the medium. So messages sent across the network got converted into a bit, or converted into bits known as a bit stream. Okay, these bits are encoded into a pattern of light, sound, or electrical impulses, again, depending on the medium in place. The destination host must decode these messages at the end in order to interpret the message. So the flow of communication is one of the things that we're going to talk about within message timing. So you have flow control. Flow control manages the rate of data transmission and defines how much information can be sent and the speed at which it can be delivered. In network communication, there are network protocols used by the source and destination devices to negotiate and manage the flow of information. So what you want to take away from this little thing, this little slide, is that protocol that is in place is TCP. And we'll talk about that the further along we go. Now, response timeout manages how long a device waits when it does not hear a reply from the destination. So your hosts on the network use network protocols that will specify how long to wait for responses and what action to take if a response times out. And then there are access methods. Access methods determine when someone can send a message. So, there are many various rules governing issues like collisions. This is when one or more device tries to send traffic at the same time and the message becomes corrupt because they collide. Now you want to think of a collision just as you think of a collision in the human network. Two cars are on the road or at an intersection and they collide. And so what happens then? So in a human environment, we stop, we get out of our car, we get our insurance papers, we exchange information, we call the police. So all of those things are governed by our rules and protocols in the human network. In networking, there are two different things that we're going to talk about a little while down the road. They are carrier sense multiple access collision detection, or CSMACD, in the wired network, and there is CSMA CA, which is collision avoidance for the wireless network. So again, some protocols are proactive in attempt to prevent collisions. That would be CSMA CA, and then others will govern how to establish a recovery method after a collision occurs, and that would be CSMA CD for collision detection. Now, message delivery may be one of the following methods. So, I could be a unicast. A unicast is a one-to-one communication. So, as you see in this picture, a unicast is going from one particular source to one particular destination. When you have a multicast, first thing that has to be established is a multicast group. You establish groups, you put devices into a group, and now you still have from one main source, but now you have to many others. So a one-to-many in a multicast environment. And then a broadcast is one-to-all. So again, one initiating source, and as you see here, everyone in the LAN would get that. Or it could be per LAN, it could be per network, and we'll talk about that in a little bit. When we talk about IP6, there is not an option for broadcasting in IP6 because IP6 is much more robust than IP4. So in IP6, when we get there, we will look at an anycast situation. Now, a note about the node icon. So this is kind of like an FYI. You won't be tested on this, not that I'm aware of. Documents may use a node icon, typically a circle, to represent all the devices. This figure illustrates the use of the node icon for delivery options. So you're still talking about a unicast, which is a one-to-one. So from source, oh, son of a gun, sorry guys. I forwarded by mistake, but you get the gist. One-to-one, just in a graphical representation. So network protocols define a common set of rules. They can be implemented on devices in software, hardware, or both. Protocols have their own function, their own format, and their own rules. And we'll learn about those once we start to break them all down in the subsequent chapters going forward. Network communications enable two or more devices to communicate over one or more networks. Network security secures data to provide authentication, data integrity, and data encryption. Routing enables routers to exchange route information, compare path information, and select best path. And service discovery is used for the automatic detection of devices or services. So as an example, being implemented on devices and software and hardware type of thing, when you're thinking about, let's talk about network security. So network security in a hardware scenario would be, I am going to secure all of my devices in a room that is locked. And the only individuals with the key to that room would be those authorized to get in that room. So that is physically placing your hardware in a locked room. Software-wise, your routers, when you get to Cisco 2, you will learn about your routers are capable of creating what is called an access control list, which is just exactly that, a list. Becky can do this, Tom cannot. Henry can do this, no one else can. So you come up with different scenarios to allow or deny. That would be done in software. Likewise, if you were thinking about a firewall implementation, a firewall, yes, is a hardware piece of device, but you would go into the software capabilities of that firewall and create your security policies. Now, devices use agreed upon protocols to communicate. So protocols will have one or more functions. So I can have addressing, which identifies the sender and the receiver. Reliability is going to provide for guaranteed delivery. Flow control is going to ensure data flows at an efficient rate. Sequencing is uniquely labeling each transmitted segment of data. Error detection determines if data has become corrupted during transmission. And application interface is a process-to-process communication between network applications. So, we, the administrators, are responsible for this first portion. After that, reliability is a TCP function. Flow control is a TCP function. Sequencing is a TCP function. Error detection runs under both TCP and UDP. And lastly, process-to-process communication between network applications. You kind of have to think of this in forms of encapsulation and de-encapsulation. Coming down the stack, the application layer is the layer that speaks to the end device. As it comes down, it gets wrapped up. Last step is to be converted into a series of bits of ones and zeros for that bit stream, going across the network, getting to the destination where the destination would unwrap that information. Again, layer 7 being the last layer to communicate with the end device. So that is why you have to be very careful when you think about this. It is communication between network applications. Now, networks require the use of several protocols. So each protocol has its own functionality and format. So this is an example of your TCP/IP model. And you see 4 layers of information. Excuse me. So Hypertext Transfer Protocol, HTTP, governs the way a web server and a web client interact, and it defines the content and the format. That information, which is your data, gets sent down to the next layer. The next layer, which is a transport layer, has both TCP and UDP as protocols in this layer. TCP will manage the individual conversations, it will provide guaranteed delivery, and it will manage that flow control parameter. Then it's passed down to the next. Internet protocol lives here at the internet layer. It delivers messages globally from the sender to the receiver. And then lastly, at the Ethernet layer, it delivers messages from one NIC to another NIC on the same Ethernet local area network. Now, protocols must be able to work together with other protocols. So, a protocol suite is a group of interrelated protocols necessary to perform a communication function. There are sets of rules that work together to help resolve or solve a problem. Protocols are always viewed in terms of layers. So your higher layers are usually noted or denoted by software happening. So these are referred to sometimes as your software layers. Meaning, would you all agree, not knowing much about networking, that if I'm going to generate an HTTP conversation, I'm going to type into my browser www.ccri.edu. That's in software. The layers below that create the conversation, so they bring up they bring up the channel, they maintain the channel, and then they delete the channel or terminate the channel at the end of the conversation. So those types of things donated as being software levels or layers. Lower layers are concerned with moving data and providing services to the upper layers. So your lower layers start to happen around the network layer in the OSI, or Internet in the TCP/IP. That is because your network layer is where your router lives. Your data link layer is where your switch lives, and your NIC. And then your physical layer are your cables. So would we all agree that those are physical pieces of hardware type of equipment? Now, there are several protocol suites that we're going to talk about. The 2 that are going to be concentrated on in this course and all throughout your history here with CCRI is Internet Protocol Suite, or TCP/IP. So this is the most common and relevant protocol used today. It is an open source protocol suite maintained by the IETF. And then, we are also going to talk about the Open Systems Interconnection, the OSI protocol model, developed by the International Organization for Standardization, which is the ISO, and the International Telecommunications Union, the ITU. Apple Talk, proprietary to Apple. Nobel NetWare, proprietary to Nobel, although we will not speak to these two. If you do see them as an option on an exam that asks you about different protocol suites, by all means pick them. On this slide, things that we will pay attention to, I am going to highlight for you. So on this slide, we're going to talk about each one of these parameters. And we will delve down into each one as we continue to go along. Now, TCP/IP protocols operate at the application, transport, and internet layers. So what we're going to see as we go forward in the slideshow is the OSI model has 7 layers of information. When they created the TCP/IP protocol model, they kind of took some of those layers and combined them together, truncating this model into 4 layers. The most common network access layer LAN protocols are Ethernet for a wired LAN or WLAN for a wireless LAN. So this figure shows an example of the 3 TCP/IP protocols which would be used to send packets between the web browser of the host and the web server. So, very first thing that happens, this host down here types into their browser. Okay, something like the minute they do that, that device starts to send out signals, and it is requesting information. It's requesting information from this web server. So somewhere on this web server, or perhaps another one, there is a file. In this example, I'm going to use .html as the language. Doesn't matter what the language is. HTTP does not care. But this device is asking for this file. This file is the HTML code created to display www.ccri.edu. Now, the next layer down is the transport layer. Transport layer, in this case, is utilizing TCP because the developer of HTTP said we need 100% reliability. Would we not all agree that if that file doesn't have all the code that I need, then it is not going to display www.ccri.edu. After that, it goes on to the internet protocol, and it goes out on the internet until it gets to the destination, where it will come all the way down into the local area network or the Ethernet or WLAN of the destination. Now, TCP/IP is the protocol suite used by the internet and includes many protocols. It is an open standard protocol suite that is freely available to the public and can be used by any vendor. A standards-based protocol suite that is endorsed by the networking industry and approved by a standards organization to ensure interoperability. So on this particular slide, we will look at all these parameters outside of your routing protocols. Your routing protocols you won't get to until Cisco 3. Everything else we will touch base on. Now, a web server encapsulating and sending a web page to the client is kind of sort of what I was talking about in the previous. So the client types in a browser address. Automatically, that end device is asking for a file that has the information to display that address. So from a sender's point or requesting point, it is encapsulating the information, meaning at each layer, it is wrapping information onto the original data that needs to be there for the end for the end device on the other end at the destination to de-encapsulate the information. So there are organizations that you need to be familiar with. So open standards encourage interoperability, competition, innovation. Standard organizations are vendor neutral, nonprofit organizations, and they are established to develop and promote the concept of open standards. So you see the ones here: IEEE, IETF, IANA, ICANN, ITU, and TIA. So, Internet Society, the ISOC, promotes the open development and evolution of the Internet. So this is kind of like your hierarchy of where things happen. Under that, you have the Internet Architect Board, the IAB, responsible for management and development of the Internet and standards. Under that, you split off into two different categories. You have the IETF, which is the Internet Engineering Task Force, and you also have the IRTF, which is the Internet Research Task Force. Under each of those, you'll see the Internet Engineering Steering Group, which has two different work groups to work with, as well as the Internet Research Steering Group, which also has two groups of research groups to work with. So the IETF develops, updates, and maintains Internet and TCP technologies, whereas the IRTF is focused on long-term research related to the Internet and TCP/IP protocols. These organizations are important in maintaining an open Internet with freely accessible specifications and protocols that can be implemented by any vendor. Now, various organizations have different responsibilities for promoting and creating standards for the Internet and for TCP/IP. So the ones in the previous slide, I would say, have a basic overview about what they do, what they're responsible for, but the two on this slide you definitely want to know. So Internet Corporation for Assigned Names and Numbers, ICANN, coordinates IP address allocation, the management of domain names, and the assignment of other information. The Internet Assigned Numbers Authority, IANA, oversees and manages IP address allocation, domain name management, and protocol identifiers for ICANN. So IANA is kind of sort of a subsidiary of ICANN. So your IP addressing schemes, you're an organization, you just opened up, you know you need internet connectivity, you would reach out to IANA and say, I need to purchase an IP addressing scheme. Same thing with the domain name. GoDaddy gets their domain names from something like IANA. You get it from GoDaddy.com. And same thing with TCP and UDP port numbers. All of those different things that we do, from an HTTP protocol, port 80, to TCP, to UDP, to services, to routing protocols, some of them are identified specifically. And when we get to the transport layer, we'll talk a little bit more about how the different ports are assigned. But you definitely want to know what these two organizations are. So the other ones here, IEEE, dedicated to creating standards in power and energy, healthcare, telecommunications, and networking. EIA-TIA develops standards relating to electrical wiring, connectors, and the 19-inch racks that are used to mount networking equipment, just like in these labs. We talked about that within Chapter 4 or Module 4. Telecommunications industry, TIA, also develops communication standards in radio, cell towers, voice over IP, satellite, and much more. And then the ITUT is responsible for defining standards for video compression, internet protocol TV, and broadband communications such as DSL. Now, here we are with our two reference models. So we have the TCP IP model on the right and the OSI model on the left, and we need to get a good understanding of how they interact with each other. So a networking model is only a representation of a network operation. It is not the actual network. So it is a conceptual thing that developers, engineers, and things of that nature would follow when they are developing their services or their protocols. So complex concepts such as how a network operates can be difficult to explain and understand. For this reason, a layered model is used. There are two layered models that describe network operations. First one is the OSI reference model, and the second one is the TCP/IP reference model. So with the OSI, as you can see here, we have 7 different layers of information. Okay, so you need to know them in order. And then on the TCP/CP, you have actually 4 layers of information. What you want to take away from this slide is in the middle, functionalities that happen at certain layers, you have to remember from one model to the other. So for instance, anything from the OSI application presentation and session happens at the application layer of the TCP/IP. The transport layer will mirror the transport layer, so they are identical in their functionalities. Likewise, with the network and the internet, even though they are 2 different names, their functionalities are mirrored. And the data link and the physical are combined in the network access layer of the TCP/IP. So benefits. They assist in protocol design because protocols that operate at a specific layer have defined information that they act upon and a defined interface to the layers above and the layers below. They also foster competition because products from different vendors can now work together. They prevent technology or capability changes in one layer from affecting other layers above and below. So the functionalities at one layer stay within that layer. They provide a common language to describe network functions and capabilities. So with regard to the OSI, if we break it down. Now again, there are 7 OSI model layers, and for some reason in industry, they are referred to as their number, not their name. This is not a standardization across the board. It's just kind of how it played out. So 7 is the application. It contains protocols used for process-to-process communications. 6 is the presentation layer. It provides for common representation of the data transferred between application layer services. 5 is your session layer, which provides services to the presentation layer and manages data exchange. 4 is your transport, which defines services to segment, transfer, and reassemble the data for individual communications. 3 is your network, which provides services to exchange the individual pieces of data over the network. 2 is your data link layer, which describes methods for exchanging data frames over a common media. And then 1 is your physical, which describes the means to activate, maintain, and deactivate physical connections. With regard to your TCP/IP, also sometimes referred to as the internet model. Again, TCP model is a protocol model because it describes the functions that occur at each layer of protocols within that suite. So your application, again, represents data to the user plus encoding and plus dialogue control. So encoding and dialogue control are actually functionalities of what happens in your presentation in session. Your transport layer supports communication between various devices across diverse networks. Same. Internet determines the best path through the network. Same. Network access access controls the hardware devices and media that make up the cables. So, controls the hardware devices. So, hardware devices here, so don't forget, this is your application presentation session, how it equates to OSI. This is your transport, it mirrors the same. This one mirrors the network. And this one includes data link and physical. So, hardware devices, at the data link layer is your switch. And media, which is your cable, lives at the physical layer. So this is how you kind of have to get a good understanding of what they're talking about when you're trying to compare both of those models. So again, a little redundancy here. OSI layer 3, the network model, directly maps to the TCP/IP internet layer. OSI layer 4, the transport layer, maps directly to the TCP/IP transport layer. Excuse me. TCP/IP application layer includes several protocols that provide specific functionality to a variety of end-user applications. So again, the application layer includes 5, 6, and 7 of the OSI. Because the OSI model separates the data link layer from the physical layer, it is commonly used when referring to, again, those lower layers. Now, some other terminologies you need to be familiar with. Segmenting. Segmenting is the process of taking a piece of data and breaking it up into smaller units. Multiplexing is the process of taking multiple streams of segmented data. So after segmentation, we can take that segmented data and interleave it or interweave it, however you want to talk about it, together utilizing the same network. Segmenting your messages has two primary benefits. It will increase speed. So large amounts of data can be sent over the network without tying up a communication link with just one particular protocol utilizing that entire link. It also increases efficiency because only segments which fail to reach the destination will need to be retransmitted, not the entire data stream. And we'll talk a little bit more about that when we get to the TCP/IP and transport layer module. So what you see here is two different colors indicating two different pieces of data or two different types of data. Now, within sequencing your messages, excuse me, multiple pieces are labeled for easy detection or direction and reassembly. So by sequencing your messages, this is the process of numbering the segments so that the message may be reassembled at the destination. TCP is the protocol responsible for sequencing the individual messages. So because messages can travel through the network on different paths, they may reach the destination out of order. If that happens, only TCP, not UDP, will put them in the correct order so that they will be completely understood. That is that reliability factor of TCP. So think of this as I send some packages to my daughter. And in old school, I actually still do this now. I am going to send Haley 3 different boxes of information. So what I would do is I would say, and I would write clearly on the box, 1 of 3, 2 of 3, and 3 of 3. So whether or not this plays out with what is in those particular boxes, my daughter at the destination could say, oh, I received 1 of 3 and 3 of 3. I'm still waiting for 2 of 3. And then when she finally gets 2 or 3, she could wait and then say, oh, perhaps I'm supposed to open 1 first because that's the first one that was sent. It's, in 2 second and then 3rd last, which may or may not be the case. But you want to think of this as the same way of sequencing. So because we have networks that can include multiple different paths to a destination. Okay, from source to destination, our packets could travel multiple different ways. Okay, so if they travel multiple different ways, depending on the parameters of that connection, a gigabit versus a 10 megabit, they will definitely be received out of order. TCP will take the time to put them back into the correct order so that all of the message is received in totality and reliable. UDP does not do that. Now, encapsulation is the process where protocols add their information to the data. So again, end user creates the data. At each stage of the process, a PDU, which stands for a protocol data unit, is placed onto the actual data. And you need to know these for each step. So for application, presentation, and session, it is simply referred to as data. Now, it's passed down to the next layer, which is the transport layer. The transport layer, we're going to find out, adds a header of information. That header is source and destination ports. So up here is what we're doing. Okay? Here is referred to as a segment. But be careful with this because transport layer includes both TCP and UDP. So if UDP is the one that is being utilized instead of TCP, then UDP's is a datagram. Although I don't usually see datagram as one of the chosen answers, it's usually always referred to as segment. Now, what happens is this whole thing now, which is a segment of data, comes down to the next layer, which is the network layer. At the network layer, we also get a header of information, okay, which is source and destination IPs. It is referred to as a packet of information. So now this whole thing is referred to as a packet. Okay? Here is where your router lives. So your routers use IPs to make forwarding decisions, which is why the header is source and destination IP. Now that whole thing comes down here to the data link layer, and it gets its encapsulation. It gets its header, which is source and destination MAC addresses, but it also gets a trailer of information. This is your error detection. Okay? This is, within that frame trailer, is an FCS field. In that FCF field is a CRC value. So your FCS is your frame check sequence. It includes a CRC value, a cyclic redundancy check. which is a value. Oops. Okay, so that value is placed into this field. Then this whole thing, which is a frame of information, then gets sent down to the physical layer, okay, where it is a bit of information, and it becomes a bit stream to be sent out over the media. Now here is where my switch lives. My switch uses MAC addresses to make forwarding decisions. Here is where my media is. It then goes over the internet and received at the destination where, excuse me, where it is then de-encapsulated. We will go over this time and time again. So an example, encapsulation is a top-down process. So the level above does its process, meaning putting that header information onto the data itself, and then it passes it down to the next level where the same thing will occur all the way until the end, until it becomes a bit stream. At the destination, the process is reversed for de-encapsulating. So as it moves up the stack. So when a layer completes its process, that layer will strip off its header and pass it up to the next level. Now, when we talk about the data link layer, it has that frame of information. Well, that frame of information has that FCS field with that CRC value. So your destination does its own mathematical value. And it comes up with that value, and it will check that value against the CRC that is in that FCS field. If those values matched, the information is just passed further up for unwrapping. If it does not match, then it is dropped. Now, Cisco wants you to know your PDUs from an encapsulation standpoint, as well as from a de-encapsulation standpoint. So make sure that you do know both. Both the data link and the network layers use addressing to deliver data from source to destination. Your network layer source and destination addresses are responsible for delivering the IP packet from the original source to the final destination. So again, network layer, you want to be thinking your router. Now, your data link layer source and destination addresses are responsible for delivering the data link frame from one network interface to another on the same network. And this is where your switch lives. Okay? So this down here at the bottom is exactly the same as what I just went through with you. Okay? So here's your data that came down from the application, presentation, and session. It got to the transport where they put in destination and source ports. Got to the network where they put in destination and source logical IP addresses or IPs. Then it came to the data link layer where they put in destination and source physical addresses, also referred to as your MACs. And then lastly, down to the physical, where it is turned into a bit stream for being sent out onto the network. Now, the IP packet contains two IP addresses. So you have a source and you have a destination. Your source address, obviously, is the IP address of the sending device, the original source of the packet. Your destination is the IP address of the receiving device, which is the final destination of the packet. These addresses may be on the same link, or they could be on remote links. Now, an IP contains two parts. And we will talk more about this, I think, coming up shortly. We will talk about the two different parts of an IP or an IP6. So for IP4, it is referred to as a network portion. For IP6, it is referred to as a prefix portion. It is the leftmost part of the address that indicates the network group which the IP address is a member of. Each LAN or WAN will have the same network portion. Your host portion in IP4 or interface ID in IP6 is the remaining part of the address that identifies a specific device within the group. This portion is unique for each device on the network. So as you see in the depiction of your layer 3 IP packet here, my source address is here. So this is going to be my network number just because I know this, so just go with me until we learn it. So this is my network address here, and this would be my host address. On this side, this is my network address here, and this would be my uniqueness. Now, when devices on the same network, or when they are on the same network, the source and destination will have the same port number in the network portion of the address. So as you see here, this is my LAN situation. So when LAN is coming off the interface of the router, that interface acts as the default gateway for everybody in this local area network. So what you want to take away from this for now is the PC1 starts with 192.168.1, as does the server. 192.168.1. If the switch were to have an IP address, it would also be, and the router's interface, so they would all be in the same network. Their individuality comes from their hosting portion. 110 here, 2 here, 1 here, and 9 here. When devices are on the same Ethernet network, the data link frame will use the actual MAC address of the destination NIC. So MAC addresses are physically embedded into the Ethernet NIC card and are considered local addressing or MAC addresses. The source MAC address will be that of the originator of the link. The destination MAC address will always be on the same link as the source, even if the ultimate destination is remote. And we'll learn more about this as we go along. So what happens when the actual ultimate destination is not on the same LAN and is remote? So what happens is your router steps in. So, like we saw in the last picture, this is my LAN. This interface, let's say it's a gigabit 1.0. That interface is my default gateway. That default gateway is on the same network. Now, remember when you did static IP addressing in your labs, you had to create 3 different parameters, which at this point are given to you. But you need an IP address. Oops, let me do it. Yeah, never mind. What is it? In this case, it's 190, 172, not 192. Nope, hold on. I'm going to gap this all up. I apologize. When you statically assign your information. Okay, let me get rid of this. So going back to my example, okay, on this PC here, I need to identify an IP address, a subnet mask, and my default gateway. My default gateway is going to be the IP address of R1. Same here for this PC. And same for here, for this server. This is simply because, just visually looking at this, would you agree that if this PC is having communication to get out, it needs to go through there? If the second PC is having communication, it also needs to go through the default gateway. If the server is having communication, it also needs to go through the default gateway. So everyone needs to be identified with the appropriate default gateway on each local area network. Now, when the source and destination have a different network portion, this means that they are on different networks. So you have 2 different terminologies you're going to learn about. You have directly connected, which is an actual physical connection to a router. So, again, these are directly connected to that router. Okay? All the way on the other side at the destination, this is another LAN. So these devices are remote. To R1. And these devices are remote to R3. We'll talk about R2 in the middle another time. Okay? So directly connected means a physical connection on the router. Okay? Remote. Oops, not remove. Is not directly connected. Okay? So think of remote as the other end of going through the internet. And so just for clarity purposes, I'm going to call this R1, R2, and R3. So when the final destination is remote, Layer 3 will provide Layer 2 with the local default gateway IP address, also known as the router's address. As you see here, highlighted with all ones. The default gateway is the router interface IP address that is a part of the LAN and will be the door or gateway to all other remote locations. All devices on the LAN must be told about this address, or their traffic will be confined to only the LAN. Again, remember your static assignments. You need an IP address, a subnet mask, and a default gateway. Once Layer 2 on PC1 forwards the default gateway, or forwards to the default gateway, the router then can start the routing process of getting the information to the actual destination. We'll talk more about that when we talk about routing. So it is important that the IP address of the default gateway be configured on each host on the local network. Now, the data link addressing is logical. So it will have a source and destination for each link. The MAC addressing for the first segment is all A's because PC1 is generating the information. So what we're going to see as we go forward in networking is IP addresses never change. Okay? We have a network admin on this side of this organization who assigns them. And we have a network admin on this side. Never the two shall meet, right? I can't go in there and change anything on this side. He can't go in there and change anything on the other side. Okay? Never change. Your data also never changes, meaning I do not start out as a web browse at the source and end up as a file transfer at the destination. It does not mean it cannot be corrupt. It certainly can along the path, but what you started out doing, be it successful or not, does not change form. What does change are your MAC addresses. And think about this. MAC addresses are embedded in your NIC card. Okay? Your NIC card is a physical piece of equipment. This router's interface has a NIC. Here, this interface has a NIC. This one has a NIC. This one has a NIC. This one has a NIC. And lastly, this guy has a NIC. Switches are not concerned with NICs. Okay? And the generator here also has a NIC. So would you agree from that generating source to that receiving server, all those NIC cards are going to be different. That's why they show you here. I'm originally going to start out with the source MAC of who's generating the information. But because it's remote, I can't deliver it. It's not going to this guy, and it's not going to this guy. It's going over here. So what happens is my first point is to send it to the default gateway. Okay? So for the first stretch, it's going from PC1 which is all A's, to the router's default gateway, which is all ones. Your router steps in and acts as a proxy. Okay? So, if I'm looking at this logistically, each time this goes through the conversation toward the destination, my first step is PC1's MAC address as the source and my default gateway as the destination. My router gets it, unwraps it, finds out where it's going. Now for this step, the router's interface on the left would be the source. The router's interface on the right would be the destination. And it would step all the way through that. So your MACs are always changing. So since data link addresses are local addressing, it will have a source and destination for each segment or hop. So this is kind of showing you exactly what I just stated to you in the NICs. So from hop to hop, those NICs will change. So your MAC addresses do change because it is a physical piece of equipment. Now, oh, this is just going through it from hop to hop like I just explained to you. So we're going to buzz right by that. So the packet is not modified, meaning that data does not change. Therefore, logical 3 IP addressing also does not change because we, administrators, assigned it. What does change is the MAC addressing because each one of these NICs has a MAC address. A very, very important concept that they want you to know.